Welcome back to the deep dive. Today, we are popping the hood on the engine of modern computing.
And not just the shiny parts.
No, not at all. We're going deep into the gears. We're talking about a transition that happened, years ago, but it completely rewrote the rule book for developers and, more importantly for us today, for hackers.
The big one.
The massive shift from 32-bit to 64-bit architecture.
It's funny, isn't it? Because for most people, that transition was just a marketing bullet point on a box at Best Buy.
Totally.
You get a new laptop, the sticker says 64-bit, and you think, great, my video editing will be faster.
Right, I can install way more RAM, my games will look prettier.
More is better. Yeah.
The consumer mindset.
And I mean, that's generally true.
Mm.
But if you look at it through the lens of a hacker, someone trying to break memory with a Stack Overflow, the landscape didn't just get bigger, it got hostile.
It got weird.
It got weird, yeah.
That's the exact vibe I got from the source material we're looking at today. We're analyzing this really deep technical breakdown of x64 exploitation. And the mission for this deep dive is to understand how those specs act as hurdles.
And weirdly, as opportunities.
Exactly. It feels like we're moving from a cozy one-bedroom apartment to a sprawling, booby-trapped mansion.
That is a perfect analogy. The core idea of a Stack Overflow shoving too much data into a buffer to, take control is the same. The physics haven't changed.
But the mechanics have.
The mechanics, the locks on the doors, the layout of the rooms.
Yeah.
It is all different.
So let's map out this mansion. When we say x64, obviously we're talking about expansion. But how big of a jump are we really talking about here?
It's a massive expansion. The most fundamental change, the one that really drives everything else, is the registers.
Okay, the registers.
Remember, registers are those tiny, super-fast storage bins right inside the CPU. If RAM is a library, registers are the books currently open on your desk.
Right.
In the old 32-bit world, those bins were, 32 bits wide.
Makes sense.
Now, they're 64 bits, that's 8 bytes wide. And with that size increase, we got a complete rebranding. The source calls it the R revolution.
The R revolution. It sounds dramatic, but it was really just a letter swap, wasn't it?
It feels dramatic if you're writing assembly code.
Fair enough.
In 32-bit, your general purpose registers started with E, like extended. You had EAX, ETX.
X, yeah.
Now, in the 64-bit world, they're prefixed with R. So we have RAX, RBX, RCX, and so on.
Okay, so E becomes R. It signifies the wider register. But here's the really cool part from the notes that I think people miss. These new 64-bit registers, they're basically nesting dolls.
Yes, I love that visualization. It's crucial.
So help me unpack that. We aren't just replacing the old hardware. We're kind of encapsulating it.
Precisely. Take RAX, the big 64-bit register. Inside of RAX, the hardware still recognizes the lower 32 bits as EAX. It's physically occupying the same space, just the bottom half.
Okay.
And inside that, it recognizes the lower 16 bits as AX. And then inside that, you have the 8-bit AL and AH.
So they didn't destroy the old registers. They just built the new ones around them.
Exactly. And that's why I can still run a program from like 1998 on my brand new machine.
Yep. The CPU still speaks the old language because the old registers are effectively still there, just hiding inside the big ones. But for what we're talking about today, we're focused on that full 64-bit width.
And it's not just the old crew getting an upgrade.
Yeah.
x64 actually introduced new players to the game.
The new kids on the block, right?
Yeah.
We used to be really cramped. We had just a handful of registers to juggle our variables. Now we have R8 through R15.
That's a lot more room to juggle data without having to hit system memory.
It is. And that extra room fundamentally changes how functions talk to each other. If you're coming from 32-bit hacking, this is the biggest gotcha.
The calling convention.
The calling convention.
Okay, traffic control. Let's break this down because the source material really hammered this point home. In the old days, if I wanted to call a function with some arguments, I would just shove all those arguments onto the stack. Correct. It was like general admission at a concert. Everybody just piles in. You'd push the arguments onto the stack in reverse order.
And the function would have to fish them out of memory one by one. But memory is slow.
Glacial compared to the CPU. So in x64, because we have all these shiny new registers, we have what I like to call the VIP lane.
The VIP lane, I like that. Who gets in?
The stack is for the overflow crowd now. The first 6 arguments of any function, they don't touch the stack at all.
At all?
Not initially. They're passed directly into the CPU registers. They get to skip the line.
That is a huge shift. So if I have a function foo, A, B, C, D, E, F, none of those variables are on the memory stack to start with.
Nope. They go straight into the registers.
Yep.
And the order is very specific. You have to memorize this sequence. It's not alphabetical.
It never is it?
Never. It goes RDI, RSI, RDX, RCX, R8, And finally, R9.
RDI, RSI, RTX, R8, R9. It feels like a video game cheat code.
It basically is. RDI gets the first argument, RSI the second, and so on.
But what happens if a function is really chatty? Say, 8 arguments. The registers are full after 6.
Then we see the overflow, pun intended, back to the old ways, arguments 7 and 8.
Or G and H in our example.
Right, those finally get pushed onto the stack. So if you're trying to overflow a buffer, you have to know where your targets live. Are they in a register? Totally untouchable by a stack overflow.
Or are they actually on the stack where you can smash them?
Exactly. You have to check the VIP list first. But let's say you navigate all that. You're ready for the classic move. Overwrite the return address.
The holy grail. Control the instruction pointer or RIP.
Right. But this is where you hit the invisible wall of x64, the zeros in address challenge.
This is the part that really made me stop and think. Because logically, we have 64 bits of address space. It's a colossal number, something like 18 quintillion bytes.
It is astronomically large. In fact, it's too large. We don't actually use all of it.
What do you mean?
Current x64 implementations only use the lower 48 bits of the address space.
So we have a 64-bit container, but we're only filling it up 48 bits worth. What happens to the other bits at the top?
They're just zeros. Specifically, the most significant 2 bytes, the top 16 bits, are always zeros in a valid user space address.
Okay, so every address looks like 0,0000 followed by the actual location. Why is that a problem? Zeros are just numbers.
To a CPU, yes, it's just a number. But think about the tools we use to exploit these systems. We're usually exploiting string functions.
Like straxb, string copy.
Exactly. And in the world of C, how does a computer know where a sentence ends?
It looks for the null terminator, the 0 byte.
Precisely. And to straxb, a 0 byte is not a number, it's a command.
Right.
It means stop, you're done, don't copy anything else.
Oh, I see the trap. I see it now.
It's a nasty one.
I want to overwrite the return address with my new address, but because of that 48-bit limit, my new address must start with 0000.
Bingo.
So I tell straxb, hey, copy this new address for me. It starts copying. It sees the very first byte is a 0.
And it says, okay, end of string, I'm going home.
And it stops. It never copies the rest of my address.
It quits early. Your exploit fails. It seems like an impossible paradox.
That is incredibly frustrating. It's like the post office shredding any letter with a zip code on it.
That's a great way to put it. But the solution comes from a really quirky aspect of how Intel chips store data.
Yes. Little endian to the rescue?
Little endian.
I know this term comes from Gulliver's Travels.
Which is just glorious nerd history. But in computing, it's about byte order. x64 stores data in little endian format.
Okay, so translate that for us non-chip architects. What does that mean in plain English?
It stores numbers backwards.
Backwards.
Let's visualize it. Your address is, say, 0x000000FFFFE3C0. To us, reading left to right, the zeros are at the beginning.
Right, the most significant part.
But in memory, the computer flips it. It stores the C0 first, then E3, then FF and those troublesome zeros.
They end up at the very end of the sequence. Oh, I think the light bulb just turned on.
It changes everything, right?
So when Strappy is writing my payload...
It writes the important stuff first. It writes the C0, the E3, all that good stuff. Then it finally hits the zeros.
And it stops.
It stops. But here's the magic trick. You're overwriting an 8-byte return address. You overwrite the first 6 bytes with your new location, then Strappy hits the 0 and terminates.
And it writes the null byte for you?
It writes the null byte. Or often those bytes were already zeros anyway. But either way, the termination action of Strappyway provides the very zeros you needed to complete the address.
That is so convenient. It turns a show-stopping bug into a feature.
It really does. You use the barrier as the solution. It's like judo.
I love that. Okay, so we had the theory. Let's get into the lab. The source material walks us through an actual exploit using a file called stack.cpp.
Right. Now, a fair warning to everyone listening. To make this work, we have to disable the safety nets.
We're driving without seatbelts.
And without brakes. For this simulation, protections like ASLR and stack canaries are turned off. And we're running the program as root.
High stakes. So step 1 involves using GDB, the G and U debugger. The source mentions a gotcha with GDB and those leading zeros.
Yeah, this trips people up. GDB tries to be helpful, so it hides the leading zeros in an address because they're redundant to a human. It'll show 0 by 7, FFFFFE3CO.
But if you're writing a payload script, you can't ignore them. You have to remember they are physically there.
Exactly. If you miscalculate your offset by 2 bytes, your exploit crashes.
Speaking of offsets, let's talk about finding that distance between our buffer and the return address.
Right. You use a tool like PETA inside GDB. You create a cyclic pattern, a long, unique string. You feed it to the program, let it crash, and see what garbage value landed in the instruction pointer.
The source note's looking for RSP or RBP plus 8?
Yeah, that's where the stack pointer is pointing at the moment of the crash. Once you have that offset, say 120 bytes, you build your payload.
120 bytes of junk, then our new address at the end.
But you don't want to aim for the exact start of your shellcode. It's too hard to hit.
Right, that's where the NOP sled comes in.
The NOP sled.
It sounds like winter sports.
It works like one. NOP stands for no operation. It's an instruction by 90 that tells the CPU, do nothing, go to the next instruction.
Oh, okay.
So you put a whole bunch of them right before your malicious code. It's like building a giant slide down to your target.
You just have to land anywhere on the sled, and the CPU slides down, until it hits your shellcode.
And boom. You have a root shell. It turns a precision target into a broad barn door.
Now, before we wrap up, there's one final puzzle in the source material that I found really clever. The small buffer challenge.
Yes. This is a great one.
So imagine the buffer you're overflowing is really small. Too small to fit your shellcode.
Right. You can overwrite the return address, but you have nowhere to put your payload before it.
And you can't put it after the return address.
Because of the zeros.
Yeah.
Remember, Streppy stops writing as soon as it finishes the address. Anything after it never gets written.
So you're stuck. Can't put the code before, can't put it after. It feels like checkmate.
It feels like it. It's a locked room mystery. But there's a third option.
Which is?
You have to zoom out. This vulnerable function was called by another function, usually main.
Right.
So main stack frame is sitting right there in memory at a higher address than where we are.
And main has access to the command line arguments we passed in.
Exactly. The payload is already in memory. It was loaded when the program started, sitting in the arguments passed to main.
That is sneaky.
It's incredibly efficient. You don't need to inject the code. You just need to find out where it's already sitting in main stack frame.
So you just point the return address to jump back to a previous stack frame?
Yes. You pivot the execution flow not to your own stack, but to the parent stack. It bypasses the size constraint entirely.
That turns the exploit from a brute force overwrite into a precision navigation challenge.
It really highlights the theme of 64-bit exploitation. It's not just about smashing things, it's about understanding the map.
It's like being a spelunker in a very dangerous, very organized cave system.
That's a perfect analogy.
So let's recap. The move to BAPIS64 gave us 8 byte registers and a massive address space.
But it also gave us that VIP lane for arguments, forcing us to check registers first.
And we learned that the huge address space creates a 0-byte minefield,
which we dodge using Little Indian storage.
And finally, even when the room is too small, we can look back up the call stack to find our payload.
The fundamental logic is the same, but the mechanics, the specific levers you have to pull, are totally unique to this architecture.
It's a great reminder that in tech, the details are everything.
Always.
Now, here's a thought to leave you with. We talked about using main stack frame, but imagine you're in a complex program, 5 or 6 functions deep.
Oh, it gets messy.
Your payload might be scattered across different stack frames. If you can only jump once, how do you chain multiple jumps together to gather the pieces of your exploit?
That is the realm of return-oriented programming, or ROP. You basically act like a kidnapper cutting letters out of a magazine. You execute tiny existing snippets of code, jumping from one to the next, until you've built your monster.
That sounds like a deep dive for another day.
Definitely. It's a whole other level of puzzle.
Thanks for listening, everyone. Keep exploring those systems.
And check your return addresses.
See you next time.